actually.
Okay. So shall I just start?
Yeah, please.
Okay. Thank you so much. I'm happy to be invited to talk with folks about African light source possibilities. I'm going to talk about my work using synchrotron radiation to illuminate the chemistry of chlorine in seawater systems. And at the end, I'll talk a little bit about how I've involved undergraduates in this work. And I also want to talk importantly about how during the pandemic, the switch to remote and mail-in operations has kind of, I think, negatively affected the training of future synchrotron scientists. So that's something I thought I might want to broach today.
Okay.
All right, so let's get to the science first. Let me see. Oops, there we go. Let's talk about seawater. So seawater, of course, is mostly water, but it also contains quite a large amount of salt. In fact, 3.5% of it by mass is salts. And of those salts, by far the most abundant ion is chloride. Chloride beats out its nearest competitor, sodium, by almost 25% by mass. So what is all of this chloride in seawater doing? Well, until now, everybody has assumed it's not doing much. This is an interesting periodic table showing the vertical profiles of various elements in the ocean from an iconic paper, 1997 Nozaki paper. And this shows the behavior of different elements. So we have a lot of elements that are depleted in the surface waters. And then as you go down with depth, their concentrations increase. So the classical limiting nutrients like iron and nitrogen and phosphorus and silicon are all depleted at depth, and then their concentration are all depleted in the surface water, and their concentrations increase with depth. But if you look at the halogens, fluorine, chlorine, bromine, they all have straight lines with depth. And this is because they're assumed to be unreactive in seawater. So the paradigm of halogens in the ocean, this is just profiles of each of those halogen elements with depth, is that they just kind of stay the same throughout depth in the water column, with the exception of iodine, which has some interesting redox chemistry, but that's not a subject for today. So today I'm going to focus on chlorine. Chlorine has very high concentrations, as we talked about. We're talking about, what is this, 500 millimolal concentrations, according to this. So why is chlorine considered to be so unreactive? Well, it makes sense because we know chlorine is highly electronegative, has a very high electron affinity, has the highest electron affinity of any element on the periodic table. So it prefers to exist as chloride, Cl minus. And once it gets that extra electron, it takes a lot of energy to make it relinquish that electron and get oxidized and bond to different other elements. So seawater is a soup of chloride ions that are generally presumed to be unreactive and very high concentration, of course. How can we use synchrotron radiation to probe chlorine? Well, first, I'm just going to talk a little bit about the carbon cycle in the oceans, and then we can talk about how we can use synchrotron radiation to look at how different elements might affect this carbon cycle. So this is a cartoon of biological carbon cycling in the oceans, and here are the surface waters. So these first roughly 100 meters are the euphotic zone where sunlight can penetrate. And photosynthetic organisms, phytoplankton, will fix carbon dioxide into biomass. So the bulk of the organic matter in the oceans comes from the biological activity of these phytoplankton. And when they die, their rotting carcasses start sinking down the water column. And through natural biodegradative processes, 99% of that solid organic matter gets broken back down to carbon dioxide as part of the oceanic carbon cycle. I am interested in what happens to the remaining 1% of the organic matter that doesn't get broken down and that sinks all the way down into the sediments. And that is a particular interest because it's one of the major carbon sinks. How do we get carbon out of the atmosphere? Phytoplankton fix it, and then some small fraction of it ends up buried in the sediments. So I'm interested in the transformations that happen between organic matter and potentially the salts dissolved in seawater as part of this natural cycle. So to look at this, I'm first going to show you some samples from sediment traps that were suspended in the Arabian Sea. So we had access to some wonderful samples from a cruise off the coast of Oman that had been preserved. And these sediment traps had basically caught the detritus sinking down from the surface waters at different depths in the water column in the Arabian Sea. So it's a way of seeing that detritus from different depths in the water column. And we can actually use synchrotron radiation to look at the composition of that material. Here I'm showing you some microscopic images. I'm sorry, I don't have a scale here of the material that was collected in these sediment traps, just to kind of bring it, give you a very beautiful picture of it. We have a lot of different biological components. So you can see these almost, they look like miniature seashells. We have foraminifera and coccolithophores, which are calcium carbonate-based skeletons. We have lots of clumpy, dark organic matter here. And too small for you to see on this scale would be the silicates, the dinoflagellates and diatoms that are also contributing to it. So we have organic matter, we have calcium carbonate skeletons, basically, and then we have also the silicate skeletons of different marine organisms. All right, so now for the synchrotron radiation part. How can we look at the state of chlorine in different environmental samples? These are X-ray absorption near-edge structure spectra that were collected at the National Synchrotron Light Source at Brookhaven National Laboratory on Long Island. And here we have photon energy on the x-axis and fluorescent yield in arbitrary units on the y-axis. So around 2,820 electron volts here, we have what's called the chlorine K edge, and that is the energy at which a 1s electron, a core electron in chlorine, is promoted up to empty atomic or molecular orbitals. And what I'm showing you here are just standards. We have aqueous sodium chloride, which would be like a saline solution. And I have two organochlorine standards where chlorine is connected to carbon. In this spectrum here, chlorine is connected to aliphatic carbon in chloropropanol, this carbon chlorine bond here. And in this spectrum here, chlorine is connected to aromatic carbon in parachlorophenol. Now, there's a difference in bond length here because this aromatic ring actually gives some partial pi character to this carbon chlorine bond. And what that means is we can use this X-ray absorption neurostructure spectroscopy to tell the difference, not only between inorganic and organic forms of chlorine, but also we can tell the difference between aliphatic and aromatic forms of organochlorine. So looking at this spectra, the inorganic chloride, because there's no covalent bond with chlorine and any other atom, has this kind of wide, broad spectrum. But when you have the presence of that carbon-chlorine covalent bond, you get this very discrete transition. And that corresponds to the transition of the 1s electron up to empty pi star and sigma star molecular orbitals associated with that covalent bond. And the energy, so this is very finely tuned, the energy of that bond varies according to the bond length. So aliphatic organochlorines have what's called the white line or absorption maximum at a lower energy than aromatic organochlorines. And that shift can be measured very precisely so that you can tell the difference between aliphatic and aromatic organochlorines. You can do this in standards, but we also are applying it to natural samples so you can see the difference between these three forms of chlorine in natural samples. So let's shoot some synchrotron X-rays at those sediment traps and see what happens. Here are X-ray absorption spectra of Arabian Sea particulates. And here I've included those three standards I just showed you at the top. So we have the sodium chloride standard, the aliphatic organochlorine standard, and the aromatic organochlorine standard. And here are three Arabian Sea sediment trap samples that have been rinsed. So when you shoot an X-ray at a sample, you're looking at all forms of chlorine in the sample. So what we did to prepare these samples was rinse away all of the salt through exhaustive successive rinsing and centrifugation with deionized water. And once all of the chloride is washed away, the sediment trap material had this beautiful organochlorine transition. You can see how these three spectra look like the organochlorine standards that I just showed you. And I'm just showing you three representative depths from the water column, but all of the spectra looked very similar for the sediment trap samples that we looked at. We looked at about 25 of those samples. What's more, the white line occurs intermediate in energy between the aromatic and the aliphatic white lines for the different standards, suggesting that there's a mixture of aliphatic and aromatic organochlorines within those sediment trap samples. So this is very interesting. We can tell the different speciation of chlorine, and we can see there's a lot of organic chlorine in those sediment trap samples. But what we can also do, interestingly, is use X-ray absorption spectroscopy in a quantitative way. So in the previous slide, I showed you normalized spectra, where we have normalized this edge jump to be a certain energy so that we can compare the speciation of all the samples. Here, though, I'm showing you an unnormalized spectrum. So around the chlorine K edge, we have these wiggles that correspond to the speciation of chlorine. But if you go far enough beyond those wiggles, the difference between the pre-edge and the post-edge in fluorescence intensity is proportional to the amount of chlorine you have in the sample, the amount of element you have in the sample. And if you're very careful about sample preparation, so you can get a very nice linear correspondence between what we call absolute intensity as measured between the pre-edge and the post-edge and the chlorine concentration in the samples. So here I'm showing you a calibration curve from chlorine standards made with sodium chloride in a matrix of polyacrylic acid. And they were made very carefully at different concentrations. And you can see this nice linear relationship between that absolute intensity as measured like this and the chlorine concentrations. So that means we can use synchrotron X-ray absorption spectroscopy not only to tell the speciation of chlorine, but to tell the concentration in samples, assuming we prepare them with uniform bulk density. So this shows you how we can quantify the different types of chlorine. Here is a spectrum. The dotted line is the spectrum, and then the solid line is the fit to the spectrum. So we can use a linear combination to tell the proportions of inorganic chloride, aromatic organochlorine, and aliphatic organochlorine that contribute to a spectrum that's mixed. So this shows you the different contributions, and then this way we can tell in this spectrum that we have 40% inorganic and then 60% organic forms of chlorine, 20% of which are aromatic and 40% of which are aliphatic. So when we look at those sediment trap samples and we break down the speciation, we find that the samples all have a mixture of aromatic organochlorine and aliphatic organochlorine in them. And there doesn't seem to be a trend with depth that we could discern from our analysis. This is looking at all of our samples. So here, another synchrotron-based technique comes in handy to tell what's going on with those aliphatic and aromatic forms of organic chlorine. And that is synchrotron-based X-ray spectral microscopy, which we did of Arabian Sea particulates. So this is a fluorescence map where we use the synchrotron X-rays to map the elemental distribution of chlorine. And lighter shade corresponds to greater concentration of the chlorine in the sample. So this is some of those rinsed Arabian Sea particulates from about almost 2,000 meters down the water column in the Arabian Sea. And then what we can do is focus the beam down to achieve a very small spot size and kind of probe the chlorine at different points in the map using microspectroscopy. So when we did that, we got the spectra that are shown in these colors here, and I've color coded this so that you can see that the red hotspot of chlorine here corresponds to these red spectra. And these other different hotspots that I have in different colors here correspond to these spectra down here. And this was really illuminating about the difference between the different forms of organic chlorine, because this very, very hot spot showed aliphatic organochlorine with a very nice clean spectrum. Whereas the other hot spots were less concentrated. You can see the noise in the spectra, but all aromatic. And we can really tell that according to the energy of the absorption maximum there. So what this shows is that we are seeing a mixture of aliphatic and aromatic organochlorine forms in these sediment trap samples. And it comes from these kind of very concentrated aliphatic organochlorine hotspots, but this kind of diffuse distribution of aromatic organochlorine hotspots. And at the synchrotron, you can also map other elements. So we went up to higher energies and we mapped the same samples for different elements that are biologically interesting in marine systems, like calcium and silicon. And here I'm going to show you those little circles again to orient you. That aliphatic organochlorine corresponds to a calcium hotspot. So could this be something to do with a calcium carbonate bearing skeleton, like a foraminifera or a coccolithophore? Whereas all of those aromatic hotspots don't correspond to any particular hotspots of calcium. And there are no hotspots of silicon corresponding to any of those organic chlorine hotspots. So that suggests that maybe this isn't from one of the dinoflagellates or diatoms. So about this natural organochlorine in marine systems, we wonder where it's coming from. Are the phytoplankton making it themselves? Is it biosynthetic? Or does the organochlorine get generated from the chemical transformations that happen to phytoplankton detritus after they die and start sinking down the water column? So we looked at some fresh phytoplankton, and here are the spectra of 4 different varieties of phytoplankton: Pavlova, Phaeodactylum, Tetraselmis, and E. huxleyi, which is a coccolithophore. And all of them show some organochlorine, but they have different concentrations, which is interesting. So Pavlova has a fair amount. Phaeodactylum has a noisier spectrum, and we can quantify how much, and it has less. E. huxleyi, interesting, has a whole lot of chloride that we couldn't liberate. That's why the spectrum looks like a mixture of chloride and organic chlorine, but it has a whole lot of aliphatic organochlorine. And this is a calcareous, a calcium carbonate bearing coccolithophore. So that is a putative link between aliphatic organochlorine and coccolithophores like E. huxleyi. We also wanted to see if we could take phytoplankton material and do some reactions to it to chlorinate it, essentially under realistic conditions in seawater. And we found that just irradiating it with a sun lamp produced a whole lot of organochlorine. These are unnormalized spectra, so the jump post-edge corresponds to the amount. And then if we throw in some interesting ingredients like ferrous iron and hydrogen peroxide, which you see in surface waters, we could get even more organic chlorine forming. So these test reactions showed that phytoplankton detritus, it starts out with, a certain amount of organic chlorine that's intrinsic to it, but potentially these reactions that occur in the euphotic systems can contribute to making even more organochlorine. So the story that we've put together shows that chlorine is actually very reactive in the marine environment, and that seawater chloride can get incorporated into phytoplankton material naturally by the phytoplankton themselves, but also through photochemical reactions and Fenton-like reactions, both in the dark and in the light. And this all contributes to the chlorinated organic detritus that we see sinking down the water column. And this might make a very stable form of carbon to be buried in the sediment. So this could have key implications for sequestering carbon in the marine sediments. And I would like to acknowledge the students who worked on this project at Marymount Manhattan College: Marissa Dunnigan, Katie Ness, and Austin Gellis. I collaborated with Larry Meyer and Kathleen Thornton from the University of Maine, who provided the phytoplankton samples. And Cindy Lee provided the sediment trap samples. Paul Northrop was the beamline scientist I worked with at Brookhaven National Lab on Long Island in New York. And again, all of the synchrotron work was done at the National Synchrotron Light Source in New York State. And these are pictures of the undergraduates that work in my lab. And I wanted to talk about how in the pre-pandemic times, it was so lovely to bring these undergraduates to the synchrotron. And since we started doing mail-in experiments, I think there's been kind of a learning loss there where the students aren't as involved in the hands-on research. So I just wanted to advocate for the possibility to get students kind of back in the lab and going to the synchrotron again, because it was so wonderful to see these students learning how to do synchrotron work. And since we started doing mail-in experiments, that's been a real loss. So thank you very much. Shall I stop the share?
Sure, yeah. So yeah, let's discuss a few things that so first, about the science, what about the the loss of whole organisms, like, whales and things like that die at the surface layer? What happens to the chlorine in their bodies, or is it just is not a significant amount?
Oh, that's a great question. We didn't study that. If you think about the organic matter, the bulk of the biological productivity comes from the phytoplankton. So that's why we sort of zoomed in on that. But other organisms certainly have a lot of organic matter that could be chlorinated. Whales are very interesting because whales tend to bioaccumulate organohalogens, and there's a lot of anthropogenic organochlorines that end up in whale blubber. So that's a whole source of organochlorines that might be natural as well as anthropogenic that could end up in the sediments. We didn't look at that, but there's been a lot of work looking at like brominated flame retardants or dioxins in whale blubber and that kind of thing, just looking at bioaccumulation of those nasty pollutants up the food chain. But yeah, that certainly there are contributions from all kinds of different organisms and sources of organic matter. We just zoomed in on the phytoplankton because it's the primary producers.
All right. So how universal do you think your results are? Do you have colleagues that are looking at other seas? And are there maybe sort of temperature and latitude, lat-long effects that might be important?
Yeah, that's a great question. People have looked a lot at bromine rather than chlorine. I talked about chlorine in this talk because it's a little rarer to look at chlorine, but people have found organic bromine in samples from all over the world, absolutely all over the world. Those are everywhere. I think that the chlorine results are probably generalized. We have Arabian Sea. It's a very, very biologically productive sea, the Arabian Sea. So it was a good chance to kind of look at these samples, but E. huxleyi are everywhere. And I think that we would find organochlorine from sources like that anywhere you look in the ocean. That's what I suspect. And then also our model reactions in the labs show that these processes can happen very easily. Even if it's not a particular organism making it, like pretty much any form of organic matter can be chlorinated readily through photochemical and other reactions. So.
What are some other methods that can maybe elucidate sort of a different angle on the story? I mean, could mass spec be on those sediment samples yield an interesting result? NMR, perhaps?
Yeah, so anything like that, you need to extract the compounds. And that's one of our limitations with synchrotron X-ray absorption spectroscopy, right? You can only tell the bonding environment of the element, but you can't tell much about the overall structure, right, of the compounds we're looking at. So yes, people are identifying individual compounds by extracting them and doing mass spec. That is certainly looking at, they can do that looking at targeted analysis and then more complicatedly untargeted mass spec analysis. But that is giving rise to findings that show kind of which organochlorines are there. And there are chlorinated lipids, there are chlorinated amino acids, there are lots of volatiles, of course, methyl chloride and chloroform and all that kind of stuff. Mm-hmm. So people are certainly using mass spec to identify specific.
All right, okay.
Yeah. Great question.
So so now your perspective on the learning loss from students not going to the lab. I first want to just congratulate you and say how impressive it is that you have these undergraduates doing frontline research that they can feel good about, just in terms of helping to understand the world and the oceans and getting publications, and I'm sure they all go on to great successes, graduate school or wherever. But the access to Brookhaven, pandemic wise, even while you're in Manhattan, right?
Mm-hmm.
So yeah, getting to Brookhaven is just hard, just in general.
We rent a car.
Yeah, so
it's not that bad. It's not that bad. If you rent a car, it's not that bad.
Mm-hmm.
We rent the car because we had to bring all the samples.
Gotcha. Yeah. So I'm in the United States, and I take the LIR out there, and then someone comes and gets me from Ronkonkona, I guess it is.
Uh-huh.
The last station before Brookhaven in the west.
Yeah.
The west side of it. But yes, so now here's the interesting thing. We, the African Light Source, have been discussing whether or not these so-called compact light sources are useful tools and a useful goal of ours. So I don't know if you know what these compact light sources are, just machines that you can fit on a university campus. And I mean, they cost, depending on what kind of building you have, somewhere between, let's say, $10 and $15 million. And so it's a campus-based synchrotron, and they've been demonstrated to perform very well for X-ray spectroscopy. Do you think that would, if you had your own instrument like that at your college, would that be sort of a useful for training and research?
Oh, that would be wonderful. Yeah, I guess you would have to have a lot of different scientists using it to justify the cost and the maintenance, but that would be amazing. I mean, the wonderful thing about synchrotron work is it's so interdisciplinary.
Right.
You can involve environmental scientists and physicists and chemists and catalysis people and archaeologists and cultural heritage people. And, there are so many applications. So on a big university campus, that would be a real hub for interdisciplinary research. And I think,
right.
Vision, that would be a wonderful thing to have realized.
Right. How do we build back in that learning loss for synchrotron sciences? Because it's becoming more and more a thing. Mail-in is for protein crystallography. A lot of people find it a good thing, actually, because they don't have to worry about customs and samples getting lost. I mean, there was a participant in this conference that missed her talk yesterday because her samples are who knows where, and she is in a situation where her visa might be expiring. She doesn't even know if she can get her samples in hand before her visa expires, much less on the rack and to be irradiated.
Wow. Yeah, I'm sorry. Yeah, I'm sorry to hear that.
So that's it. So, but how do we build back in these learning losses?
I don't know. I think it's really bumming me out. I have to tell you, because I just saw the students at the synchrotron, their eyes being open to science and research scientists, and just feeling how important it was. And I think it's a real deficit now since we started doing the mail-in. I mean, it's easier in a way. You have to pre-plan the experiment and think through everything that could go wrong. So maybe that's good, but then you're not there to troubleshoot. And, if something does go wrong, then you have to figure out what happened later. So there's that. I think that might negatively impact the science, but I think the major negative impact comes from the young scientists not getting that crucial hands-on training and experience.
Yeah, and we're finding, I mean, that's a problem. But people getting visas. So, even going from point to point within Africa can be problematic, just on the basis of visas. And then, as we find, even with the US government, um, because there's a dearth of personnel, so, people retiring, and, Congress doesn't like to replace employees. Well, I'm in the United States, you're in the United States, and you can see even with the IRS, they're facing all these retirements, and there was a bill to replace them over 10 years, and they got demagogued as, Biden wants to wants to hire 1,000 more IRS agents to audit you or whatever, when it was really a thing of replacing them over 10 years. But the same thing is happening to the State Department. These are people who process visas. I mean, there's just a dearth of personnel. So we have a huge problem in that regard that is impacting learning, collaboration, science production, and probably the only solution we can come up with as scientists, something that we can control, is more home laboratory based equipment.
Right.
And I'm wondering, is home-based laboratory equipment, I mean, as electronics and photonics get to be more advanced, does that make it more possible? I mean, so if there was an XAS rig that you could have at your college, how much do you think you would have to spend? And isn't that something that you would even want to accommodate?
Oh, well, I think working at a small undergraduate only institution is probably out of my reach. But if somebody were at a research oriented institution, now there are lab-based XF systems that don't require a synchrotron.
Yeah. So there's an easy access. Jerry Seidler's easy. I guess
Yeah.
he's not with the company anymore, but
Yeah,
yeah.
exactly. So I'm all in favor of anything to broaden access. I know for those systems are no good for chlorine, for instance, but they're useful for other applications. Anything that you can do to, as all of this technology advances, I think access is going to get broadened, and people are going to be able to do things right in their own labs, even without a synchrotron, that are very element specific and revealing. There's still so much we don't know about different systems, and so much science to be done. And the more capabilities you can plop down in different places, the more people you can get doing work and asking different questions, and the better it's going to be for science as a whole. So I think
So that's interesting. You say they're not good for chlorine. Why is that?
so. There's something about, I don't remember the exact reason, because I asked Jerry Seidler about this, whether like this kind of spectra I showed you in the talk today wouldn't be possible.
Wow.
Using those systems yet, but the yet is key, right? There's so many advances that, in 5 years time, that could be totally different. I don't know
Okay. Yeah, we'll look that up, because so the African light source, we are trying to, get a handle on lab-based, home-based, instrumentation, and these I don't know if you heard of this company called Lincian, the Lincian machines.
Okay.
They made like what's called tabletop synchrotrons.
Right.
I mean, if your table is the size of a of a building, but they sort of went out of business because the market for their machines was not developing as fast as their cash flow was leaving them. So they needed a lot of upfront capital, and they just ran out of it. But yeah, we're trying to get a handle on, what's the affordability, what's the advantages, does it take away from getting people to synchrotrons, and getting students to synchrotrons is Well, the problem there is not scientific. It's not even budgetary in terms of science budgets. It's bureaucratic. It's just the way the system is. We even tried to get uh, some African heads of state and some science ministers into Brookhaven during the UN General Assembly. So the big UN thing that's in Manhattan.
Yeah.
Right. So Brookhaven has such a cumbersome visitor badging process.
They do.
That I mean, it was like difficult to get a head of state to go, and then with a single head of state,
did you
manage
an
entire entourage of even U.S. security agents? So when a head of state comes to the United States, they get like Secret Service protection, right? So even the agents, the Secret Service agents, needed to be badged, and of course, they didn't want to be bothered with that. They didn't care. I mean, they're like, why are you creating extra work for us? So it was just hard. And it would have been great to have, an African head of state to see a synchrotron, to see what's happening there. And especially at Brookhaven, where there's actually a couple of Ghanaians that work there. So to have the Ghanaian president to be there would have been very nice.
Oh, it didn't happen in the end?
Didn't happen in the end. I mean, it was actually a lot of things because when this was happening, this was last year. Also at the same time, the county, Suffolk County, whatever county it is that Brookhaven is in, I think it's Suffolk, right?
Yep.
It became a COVID hotspot. So now no one was interested in going out there. And then they, because even while we were entertaining the idea, I guess DOE Central decided no visitors to Brookhaven whatsoever because of the COVID hotspot. I guess the federal government didn't want to be involved in transmission of COVID to whomever, so they basically shut Brookhaven down, and I think there was like protocols as to even who could come to work, who of the employees could come there.
Yeah, I still get all those emails. They have really stringent COVID policies.
Yeah, really strict rules. So so the whole thing didn't happen. So even as we are lamenting this environment that we're in, the learning losses and all that, a lot of it we have to think about in terms of how much of it is actually short term.
I don't know.
And
I'm worried that the mail-in is permanent for a lot of different beamlines. I mean, this is
a
little sad, just nostalgic and worried about the students of the future.
Okay. Well, look, the African Light Source, we have a monthly sort of colloquia series that, I mean, we do everything by Zoom. So this is almost a permanent way of operating. We do it by Zoom, just like, now it's a conference, the audience is a little light. But we'd like to invite you back to give this talk again and really focus more into how your undergraduate students are performing here. Because that's really exciting.
Yeah, I would be delighted. I love talking about it. I'm so proud of these students. Most of them are women, and it's just they go on to amazing things, and I would love to talk about it. I can also talk about some new stuff too.
Yeah, and then the University of Cape Town is actually pretty big in oceanography. They have one of the best oceanography programs in the world, I guess. And I don't know if you've ever been to Cape Town, but it's beautiful there. It's a cross between San Francisco and Honolulu.
Oh, I've heard amazing things.
Yeah. So yeah, we'll have to invite you to South Africa or anywhere in Africa, and there are conferences. There's something called Science Forum South Africa, which is great. I don't know how your semester ends, but it's usually like the first week in December.
Okay.
Anyways,
I would love that.
It is
anytime.
it is not a bad pre-Christmas trip if you so you could conference a little and vacation a lot. This is what you say.
Nice. I would love that.
Yeah. Well, thank you for coming to our conference, and we'll definitely have you back, and we'll keep in touch. And very excited about your work, and I will actually do some reading So I never watch television. All I do is read. So I will do some reading of some more of your work.
Can you tell me your name?
My name is Lawrence. I'm Lawrence Norris.
Okay.
So I'm on the program committee for the African Light Source and the African Physical Society.
Very
So
nice.
and we have, and I don't have a camera on this particular machine that I'm sitting in front of, but I'll send you an email. And like I said, we do have colloquial experiences, and we have a biophysics conference. So this is sort of biophysics-y. I mean, I was trained in biophysics, so I said, I have a very wide definition of biophysics. So yeah, we'll hope to interact with you again.
Thank you. Thank you so much. I really
Okay, thank you.
Thanks.
All righty. So I think that concludes the sessions of this morning. So we'll see you guys later. All right, thanks.